Hey everyone, welcome to the second video on cylindrical shells, and in this one we want to take a look at another example, this time with a yellow object, and also make some comparisons between disc washers and shells. Right here you have your yellow object, which represents this parabola kind of rotated around an axis, some computerized drawings as well that you might see in a textbook or website. Um, First thing we're looking at again is where's the axis of rotation, and you might be able to tell, like, I have a parabola kind of sitting right here, um, goes up, so kind of a rough shape right there, but that axis of rotation as this goes around is going to be right there at the bottom of the parabola. So this is just going to rotate around and around as we go through. So we're looking right here on the x-axis. So there's our x-axis, and that is our axis of rotation as well. So we're going to say y equals 0, or you can just write in x-axis on that guy. We're also going to draw a sample rectangle to rotate, and if we're using shells, that's going to need to be parallel. So you can go ahead and pick any height you want. You could do up here, down here, so whatever height you want to draw it at, fine. But I'll just put it in right there. So this is our sample rectangle. So this is going to have a small change of height, dy, and then I'll go ahead and rotate that. So this is going to get rotated around that x-axis. So it looks something along those lines. Just like before, right? So this is the volume of the general sample shell that we want to find, and we talked about this in the last video, but basically if you unwrap this you get the circumference, 2 pi r, where r is that radius from the axis of rotation to this rectangle. So we'll kind of define what that's going to be in a minute, and then times the height of this cylinder. So that would be, in this case, this horizontal stretch from this x value on the left to this x value on the right. So we'll go ahead and put that in. So volume of a sample shell is going to be pi r h times dy. And what we'll see in the case of the r for this one is we're going to go from our axis up to whatever this height is. And normally, right, when you're plotting points, you're just going to say, all right, well, how far am I going to go? I'm going to go from here up a distance y, so over x, up y. So just that vertical height from the x-axis is always just going to be a distance y. So in this case, we could say r actually equals just a distance of y. So that's what we'll get for our r value. So we're going to put that in, 2 pi times y. And you don't want to put in the definition of the function, right? So you don't want to change that into this function definition, because everything is going to need to be in terms of y for this dy. So we already have it as y. There's no need to change it into x for any reason right there. However, the height, we are going to need to change that in terms of y. And right now, it's just the difference between this x on the right minus this x on the left. So we could say x right and x left. Go ahead and put that over here. And I need the difference between those two to get that height. So let's go ahead and kind of put that over here. So the height is this x on the right minus x on the left. All right, well, the first problem is, right, I don't even have an x, right? I don't know what x is in terms of y on this guy, so I need to replace these with some y definitions. So I'm actually going to have to go through and solve this equation for x equals, just to be able to plug in some stuff right here. So let's go and do that, say down here in this bottom half of the grid. So if I do that, I have, let's see, y equals, that's negative x minus 3 quantity squared, 4. And I'll go ahead and subtract the 4. So we get negative 4 plus y equals this negative x minus 3 squared. I can divide or multiply by negative 1 both sides, so this will give us a positive 4 minus y equals this x minus 3 squared. So again, dividing everything by negative 1 there. And then I can do a square root, and then I'll be almost done after that point. So don't forget when you do the square root, the plus or minus square root times y is this x minus 3. And then add 3 to both sides, so I get 3 plus or minus that square root of 4 minus y is my x. Right. And we talked about this before when we were doing the discs with the red objects, that I have this midline of 3, either plus or minus that root to get to each side of the parabola. But those are the values I need to put in for the XR and XL. So we'll go ahead and do that. So the H is going to be this one on the right, so 3 plus the root. So let's go and put 3 plus that root 4 minus y, and then minus, we need the x on the left, so that's 3 minus the root, so 3 minus that square root 4 minus y. And I can distribute the negative, right, so this is going to give us 3 plus that root, and I'm just going to kind of shorthand this step, minus 3, and then plus that root again. Negative times negative will be plus, and that 3 and negative 3, those are going to subtract out, so those are gone. And we have basically this root plus the same root that's right there. So we get 2 times that square root of 4 minus y. So that would be the height of this rectangle at any particular height y. I can always get the length or the height of this rectangle as 2 times the square root of that 4 minus y. So that gives me that h in terms of y. So go ahead and put that down here in my sample shell. So this is going to be times 2, and I'll worry about simplifying that in a minute. So 2 square root of 4 minus y. Alright, from there go ahead and if I want I can just multiply these 2 and 2, give me 4. So we get 4 pi y times that square root of 4 minus y dy. And essentially that's what we're integrating over this values of y. So y goes from 0 up to 4. So we'll go ahead and put that in my integral and calculate that out. So we got integral 4, it's going to be my volume, and we got the 4 pi y square root of 4 minus y. And since we're basically using technology for most of these, if you just wanted to leave it, with the 2 separated, you could. Kind of up to you on that. So let's go ahead and calculate that real quick. I went ahead and put that into Desmos. Integral 0 to 4 pi y square root of 4 minus y dy. And we get this 107.233. So that is the value that you should get for that integral. These should match the other volumes we found with discs and washers, so if you want to compare those, you can. They should match up, just a different method of doing it. Alright. Some things to think about, right? If you compare the work for objects 3 and 4, which was the green and the yellow, what did you notice? So, one, you might have noticed, right, shells for the green one is a lot easier than shells for the yellow. The reason for that, right, is because I had to go through all the work of rearranging, in terms of X on this one, where the green, it was just, take the Y, plug it in, because we had it in DX, so it's just a straightforward plug-in for that function. Whereas this one I had to rearrange everything to try to find those X values and then subtract, and finding that H was just a lot more difficult for this one than it was for the green one. So that's one thing that you might notice on there. If you look at also the scenarios from the disc and washers handout, and shells. What rule could you make for determining if you're using discs, washers, or shells? So I'll let you think about that for a little bit. Go ahead and pause the video, and then we'll come back in and talk about it. All right, so if you've thought about it, a rule that you could use for dishwashers or shells is basically looking at the rectangle you draw, right? So if I draw a rectangle and it is perpendicular to my axis of rotation, I know I'm going to be using washers in that case. And you can draw it out, and see you're going to get a washer for something like that. If it's not touching. If it's touching, right, then I'm going to get a disc. So if my sample rectangle is always touching, right, never has a gap, then that's going to give me a disc for something like that. So if I'm perpendicular, I know it's going to be a disc or washer, and I just have to see, is there any separation at some point between the axis of rotation and my rectangles? If not, then I'm using discs. If there is somewhere, then I'm using washers. Whereas shells, right, that is always going to have kind of this parallel rectangle to the axis of rotation. So shells will always do something like that. Again, it may be a vertical line that you're rotating around, but shells are always going to be parallel for those guys. So looking at am I parallel or perpendicular to the axis of rotation is something that can definitely determine if you're going to be using a disc, a washer, or a shell. This other question, given a region and axis of rotation, which would be better to choose first, your method or your sample rectangle? So again, go ahead and pause the video, think about it, maybe write a response down, and then see what that should be. Alright, so for this one, if I'm given a region axis rotation, which should I choose first, method or rectangle? So you might say, well, I just like discs and washers better. I'm just always going to use that. There are some cases where you may have to rearrange some things, and it's not that easy to rearrange the equation. Like with the blue one, we could do it, but there's other regions that aren't that easy to solve for x in terms of y, or vice versa. So usually what's best is to pick your rectangle so that you don't have to rearrange things. So in this case, definitely the rectangle. Easiest to do first. Draw it so you don't have to rearrange a bunch of stuff if possible. And then you can look at, all right, am I parallel or perpendicular to the axis of rotation, and decide what method to use after that. So rectangle first, then decide your method. And we'll look at an example of that in the next video. One where you can't really do it both ways. Some regions you can do either with a shell or a washer, and it goes okay either way. We'll look at one next time where there's definitely one method that's going to be better than the other. And then which is easier to use, washers or shells? So this one, again, you can think about for a second if you want to pause it. And you might have a preferred method that you like better, but I would say it's probably not always easier to use. It's going to depend. So this one depends on whether or not you have to rearrange that equation and how easy that equation is to rearrange. If it's not too hard to rearrange, it might not be a big deal to just switch it. But some equations are going to be a lot more difficult than others. So it depends. We'll say how easy rearrange the equation if necessary. And again, you're always shooting for, right, hopefully I don't have to rearrange it if I've picked my rectangle correctly, but if you're always picking, I just want to use a washer, then there might be some rearrangement involved. All right. Check out the next video with some examples of a little bit different equations, and especially this one where it's not an x or y axis that you're going to rotate around.